morning to everyone. Today we'll start with new topic which is greedy algorithms, which is basically module 3. That's what we'll start with. So greedy approach basically means in the given circumstances at the given setup, whatever immediate solution seems better, pick it up and keep building it up. And for a good number of problems, the greedy approach works better. It gives you immediate solution. It works out. But greedy approach does not necessarily always give you optimal solutions. But it does give you solutions, and we'll look at, analyze it, how does greedy approach works. And again, if you have any questions, please feel free to ask. You can ask the question in voice or you can raise in the chat box. Either way, and we should be fine. So textbook is given in both our Levitin's book or our Sani, even in Corman, read any one of those and you should be fine. So primarily how does my greedy algorithm work? It basically says make the choice which is best at the moment. And just give you the basic example there. Let's say I'm feeling a bit hungry and I want to eat something. I go to canteen. Now, if I'm hungry, I like to eat whatever is available rather than waiting for something which comes 10 minutes later. So do I wait for something better to come up 10 minutes later, more tasty, or something that I'm feeling hungry, I need to eat quickly? So greedy approach would be get something quickly and then see if something else comes later, do that, or don't wait. So in that sense, the primarily greedy approach is that you, given the set of problems, given the set of inputs, pick up one input available which seems best, and then you go from, let's say if you are hungry, go to canteen, you have a cold drink, you have a biscuit, you have a idli, probably take a idli, and once idli is taken, if you're still hungry, you might take something else, and that's the approach you'll basically build up. And we'll look at this example by taking few examples. How do we begin? So clearly, we need to decide how to pick the next piece. Given the 5 choices, as I said, the canteen, you have a biscuit, you have a cold drink, you have a idli, which you want to choose. If you are hungry, you'll probably choose idli. If you are thirsty, you'll take a cold drink. So it depends upon what you're trying to, which gives you immediate gain, maximum gain, or maybe lowest cost. You want to conserve energy, so which would be cheaper. So based on your objective, you decide what immediate next move to make and decide upon that. So whatever you decide, that should either maximize your benefit or minimize your cost. And what we expect is if we keep taking this local decision one at a time, and then this may give me the total optimal solution overall. We expect that, but it need not be true. I'll give few examples there. In some cases, it may work out. In some cases, it will solve the problem, but it is not going to give you optimal solutions. Now, the challenge always remains, how do we decide which choice is optimal? How do we make a decision on that? That means we need to have some criteria to define that as long as that criteria is satisfied, I should use that. We need to define criteria which we call as objective function, which decide what choice we need to make. Having made that choice, that input is done. Now look at what the next choice available. Let's say I need to build a cricket team. So I look at which is the best player to pick up. Then I look at the next best player to pick up. Now, does that give me all the best team? Maybe, may not be. If I keep picking all the batsmen, then I may not even work out to get a great team because we don't have a bowler, we might lose out the game. So, but at the moment you define the objective function, what the objective function is, pick up that and then make a decision, keep deciding locally and keep repeating the process. And once you take a decision, you don't use the decision back. And decision is taken, build upon it, and that is primarily the greedy approach. So the benefit of the greedy approach is it is simple and easy to design the algorithm. It's not too complicated. And because it's simple to design, when we do our time complexity analysis, because algorithm is said we always have to do our analysis, what is the cost complexity, and deriving the cost complexity analysis becomes comparatively much easier, and that's the benefit it gives us. And for divide and conquer, it may not be easy. Sometimes we look at that part, but divide and this thing depends how do we divide the problem and how are we conquering it, joining the solutions together. But again, we'll take few examples. We'll look at about 4 or 5 examples of greedy algorithm approach and see how does that solve it. The main disadvantages is that whatever algorithm we're choosing, do we know it's always correct? First is the second is it may not be optimal. Does it even give us the correct answer? May not be. And let's look at how will that work. Sometimes that may not even meet the requirement, and we see how do we go about doing that. So let's look at a problem what we call is a coin change problem. Coin change problem is, let's say you are a shopkeeper and somebody gives you money, somebody buys stuff from you, and you have to return back the change. Your objective is you have to give him the whatever exact change required, and you want to dispose of minimum coins. Let's say assume you have a good amount of coins. The coins available to you are 1 rupee, 2 rupee, 5 rupee, 10 rupee, and 20 rupees. And assume you have enough coins of this denomination. You have enough coins of rupees 1, you have enough coins of rupees 2, you have enough coins of rupees 5, and so rupees 10 and 20. And somebody gave you 100 rupees, he buys 57 rupees worth of stuff, and you need to return 43 rupees back. So what kind of coin you should choose? One can always say, look, I can pick all coins of 1 rupee, give him 43 coins, it meets my requirement. Or I can take 21 coins of 2 rupees into 2, this gives me 42, and then I say 1 coin of rupees 1 and again get 43. So what we're trying to do is, shopkeeper would like to keep maximum coin with self, so his objective would be, first it has to give exact change to the customer and do so with minimum number of coins. Now, do so with minimum number of coins is what is the criteria. Now, let's look at typically you don't want to try all possible combinations and you take a greedy approach. And greedy approach would basically work saying, look at the coin with highest denomination. We need to give 43 rupees. So I take my highest denomination coin, which is 20 rupees, subtract 20, I am left with 23 rupees. So I am left with 23 rupees. Then again take the highest denomination coin, minus 20, I am left with 3 rupees. Now, can I pick 10 rupees coin? No, because that will give more than. So far at this point, I'm yet to pay 3 rupees and 40 rupees is done. So if I take 10 rupees coin, I'll end up giving 50 rupees, that won't work. I cannot take 5 rupee coin, that also won't work. So next I take is 2 rupees coin, and so sorry, I am left with 3 rupees here. So I take, as I said, I have 43 rupees to be given. I first pick largest coin 20 rupees, I am left with 23 rupees. Then I again pick 20 rupees coin, I am left with 3 rupees. Then I pick largest coin, which is 2 rupees, I am left with 1 rupees. And then I pick 1 rupee coin, I pick 1 rupee coin, and I am done. So total coin I have given is 2 coins of 20 rupees, 20 rupees coin, 20 rupees coin, 2 rupees coin, and 1 rupees coin. So total coin I gave is 4. And this is what we're basically saying. So that means to give 43 rupees, 2 coins of rupees 22, 1 coin of rupees 2, and 1 coin of rupees 1, and we end up giving total of 4 coins. Is the solution optimal in this case? Yes. Now look at assuming if shopkeeper has the coin denomination of 1 rupees, 2 rupees, 5 rupees, 10 rupees, and additionally he has another coin 25 rupees. Now I would like to ask you, does my greedy approach still work? If I were to take a greedy approach, that means take the largest coin, how many coins we need to be giving to meet our requirements of 43 rupees? Can you quickly work out and tell me how many coins we'll end up taking if given that these are the coins available to us and we still follow greedy approach? What is the coin number of coins required to give 43 rupees? Spend about 2 minutes, work out, give me the solution, put in chat box or speak out and tell me what coins you choose and how many coins. Just work out yourself. Anyone has worked out? Would like to speak out? Sri Vidya, any answers you like to give? Nikita would like to give the answer. How many coins I need and which denominations? You have to unmute your mic before giving the answer. Yeah. Nikita gave 25 plus 10 plus 5 plus 2 plus 1. So answer, if I take greedy approach, my answer is I take one coin at 25 rupees, then one coin of, I cannot take 20 rupees coin anymore, then I take 10 rupees coin, this gives me 35 rupees, then I take 5 rupees coin, this gives me 40 rupees plus 2 plus 1. That means total number of coins I am taking is 5. If I didn't have denomination of 25 rupees, if I had only these denominations 1, 2, 5, 10 and 20, then I was done with 4 coins. But the moment I got another coin of 25 rupees, my number of coins became 5. That means I ended up giving more coin. My greedy approach worked in the first case. The approach did not work in the second case. Thanks, Sri Vidya. Thanks, Nikita. I give the answers. So what I'm trying to say is, greedy approach, it works. It gives me the solution, but it necessarily does not give an optimal solution. And that is precisely what I'm basically trying to say there. Now, let me look at the problem differently. Does the greedy approach always gives me solution? And the reason I'm asking is, assuming you do not have 1 rupee coin at all. Assuming you do not have, let's take this case, first case, let's say you do not have 1 rupee coin at all. Can you still meet out the requirements of 43 rupees? Assuming your coins are 2, 5, 10 and 20, I want to give 43 rupee change. Using a greedy approach, will I be able to give 43 rupees? Dhruv said no. Thanks, Dhruv. Now, can you tell me what the answer would be? Assuming I need to distribute 43 rupees, what would the optimal solution be to give out 43 rupees? Anyone like to answer? Assuming my coins are 2 rupees, 5 rupees, 10 rupees, 20 rupees, and I need to give 43 rupees back. So, what are the coins I need to give to meet my requirements of 43 rupees? And how many coins I would need? And would like to answer Monica or Likhita? So the two questions, why it is that greedy approach doesn't work? And second question is, what is the optimal solution if I have only four coins of 25, 10, sorry, 20 rupees, 10 rupees, 5 rupees and 2 rupees? Awaiting an answer, respond 1 minute, give me the answer. KK Pavitra, first, is it possible to give 43 rupees? Anyone like to answer? Dhananjay, Manvit, or is it so difficult? Amravati, no, it is yes. Amravati gave an answer. It is possible to give the answer, and answer is 20 plus 10. Sorry, 20 plus 10 plus 5 plus 2 plus 2 plus 2 plus 2, and this much is 43 rupees. And total number of coins is 3 plus 4, 7 coins. But if I were to take a greedy approach, then this will not work. Why this will not work? Because first I take 20 rupees, then I take another 20 rupees, I'm left with 3 rupees, and then I take 2 rupees, I left with 1 rupees, and no 1 rupee coin. So remember what I said, greedy approach may not even give you a solution at all. Forget about the optimal. So we have seen three cases in our case here. If you look at, in this case, if my coins are 1 rupee, 2 rupee, 5 rupee, 10 rupee, 20 rupee, greedy approach gives a solution. It gives an optimal solution. If I have denominations of 6 kind, greedy approach gives a solution which is not an optimal one. And if my coin were only 4, 2, 5, 10 and 20, greedy approach doesn't even give me solution, forget the optimal one, even though the solution exists. The point I'm trying to make is not necessary that greedy approach always gives you a solution, but we'll see most of the cases when you deal with the problem, greedy approach is simple to follow, it is easy to implement, and we can proceed, and that is what we'll basically look at in our case. So let's look at what the objective in our case. What is my objective function? Objective function is I should choose coins so that I should such a coin so that this amount to be paid keep getting reduced, and I should be able to meet exact 43 requirement. So choose a coin such that the amount of to be paid keep getting reduced, and when it becomes 0, I am done. That's the way we look at. Let's look at another problem using greedy approach. Let's say you want to have a party at home or you want to invite three friends. So you are at your home here and there were three people to invite. A, person A, which is 10 kilometers away from your home, person B, which is 11 kilometers away from you, and person C, which is 12 kilometers away. So A is 10 kilometer, B is 11 kilometer, and C is 12 kilometer. And further, B to C is 2 kilometer. B to C, so look at, as I'm saying, home to A is 10 kilometer, home to B is 11 kilometer, home to person C is 12 kilometer, A to C is 8.5, A to B is 8, and B to C is 2. Now, if I were to take a greedy approach, an objective is I should invite all three of them and come back home. Invite all three of them and come back home, and I want to travel minimal distance. And I need to visit each friend once. So how do we go about? I take a greedy approach. I see among A, B, C, who's nearest to me, I go to A's house. So when I go to A's house, I go 10 kilometers. From A, I see which is the nearest. I see B is 8 kilometer, B is 8 kilometer, and C is 8.5. So I first, from home, I go to A. Then from A, I go to B, which is 8 kilometer. From B, I go to C, which is 2 kilometer. And then from C, I need to go back home, which is 12 kilometer, and total distance is 32 kilometers. But this is not optimal if I were to take a different route. And different route is, if I from home, I have gone to B first, which would have been 11 kilometer. B to C would be 2 kilometer. C to A would be 8.5, and A to home is 10, and this basically is 31.5. So that means if I were to take a greedy approach does not give me optimal solution where other approaches give me better, but greedy approach does give me a solution. And that's the point I'm basically trying to make. This is how to go about. My criteria is go to nearest house, figure it out, and work it out. We already done that. So let's look at what is the basic greedy approach algorithm, what is the paradigm is. You are given an input, like in the coin we have seen input is 1 rupee coin, 2 rupee coin, 5 rupee coin, and so on and so forth. And in the case of our visiting a friend, input is distances to each house. We know that. And now we select an input based on some selection criteria, whatever we try to use based on the objective function. Now, if that selected input leads to feasible solution, we take that input, proceed next, and keep repeating it, and else pick up the next input, reject that input, and continue and see can you find it. And what we select depend upon what is my optimization measure. An optimization measure in coin change was minimum number of coins. But while I need to meet the exact requirement, and that could be my objective function. So let's look at, do always only one solution? No, sometimes there could be multiple solutions, and we look at. So primarily the greedy approach would be is what we call it a subset paradigm. Given a set of inputs, like in coin change, we say my input was 1 rupee coin, 2 rupee coin, 5 rupee coin, 10 rupees coin, and 20 rupees coin at the 5 inputs. So we have a set of this thing, we follow subset paradigm, take one thing at a time, and so approach is greedy approach given this set, assuming this is an array of size n, you have n inputs. Initially my solution is empty, and then I look at, for each of the array element, look at type x select a, which is the best one you select, and see if this selection, when I do a selection x, does it meet my requirement, does it lead to my solution? If so, add this solution x to the solution. If not, discard that input and continue, and finally you'll get this solution. So typically, if you look at sub-analysis is, I do a select function from the input and removes it and value is assigned to it. And there's a feasibility check, is it workable? If so, adding it to it and then continue there. And union means keep building the solution. And let's look at this algorithm to our coin change problem and how does that work. So look at the coin change problem. Assuming enough number of coins for each denomination are available, initial solution is empty because I need to give a change. So at each stage, we choose one coin, and what we do, add to the change, and keep looking at the next coin. Now my criteria is greedy criteria, meaning take the highest denomination coin. So greedy approach is highest denomination or highest value coin, because when I take highest denomination, the amount of change to be given will always keep reducing and basically decrease. It should increase the amount of change as much so that I meet the requirement, and that's what basically do. Feasibility check, does it meet my requirement? I should exactly meet a requirement of paying the change, no more and no less. I have to give the equal amount. If I pay more, I end up losing it. If I pay less, my customer would be unhappy. So I have to give the exact change. And my objective is to use minimum number of coins. So we look at the algorithm, basically like following. I given the coin, let's say 1, 2, 5, 10, 20, 50, 100. Algorithm coin change. Start from the highest, we say start from highest, assuming these coins are sorted. Sort them, start from the highest denomination, pick up that index and see if the amount is greater than the coin. Yes, pick up that amount, and the result is basically whatever. I'm looking at the number of coins because I'm trying to put the number of coins. So for this index, I'm putting this number of coins. That will be 100 rupees coin. I'll use one. If this and decrease the amount. So I keep decreasing amount. So let's look at and then we'll keep decrementing the index and keep going further. So let's look at how does it work for our coin change case here. So basically when I put my amount is 43 rupees, 100 would not work. So index is greater than 0. Index start from 1, 2, 3, 4, 5, 6, 7. Index is 7. Amount is greater than the index, not true. So we basically go back, index becomes 6. Index greater than 6, which is 50. 50, 43 is greater than 50. We don't do the, then come to index. Index becomes now 5, 20. So 20 index is basically 5, 5 greater than 0. Amount is 43, which is greater than 20. So I say index of 20 becomes 1, the 0. Amount becomes 23 rupees. Go to the while loop again. This becomes plus 1, which is 2. So for the 20, index value becomes 2. Amount becomes 3 rupees. Then I go to the next one. Now I take the index becomes 4, which is 10, not applicable. Next time index becomes 5, not applicable. And proceed in this way. And finally, I'll end up doing it. You can work out the example yourself. If you were to give coin change of 252, how many coins you need, and the algorithm would work accordingly. Let's look at another example of greedy approach. I'm giving simple examples so that you understand how does greedy approach work. Let's consider that colony has number of houses and they get a water from a water tanker whose capacity is T. Now each household has a container of size Ci, and objective is that we need to supply water. And I'm a politician, I want to make sure, because I get votes, I want to supply water to maximum houses. And at the same time, when I send a container, I want to get minimum water back. And this is my objective. Further, if a house doesn't get the full container, house will not be happy, they will never vote for me. So either house should get full water or whatever container bucket they got, or no water is fine. Giving them half a bucket of water does not work. Given that, I would like to do So assuming I have a case where my tanker capacity is 150 liter, I have three houses, one requires 50 liter of water, second requires 60 liter of water, third requires 150 liter of water. Now if I were to take a greedy approach meaning I need to satisfy maximum number of people. So I'll start with 50 liter, then I'm left with 90, then I take 60, I'm left with 40, I satisfy two households, but I'm returning back 40. And there's a cost there. If I were to take other approach, take the highest bucket size, then I take 115 liter, I'm left with 35, and I'm not supplied to anybody else. So I supplied only one house, the wastage is less. Now the politician decide because returning less is better for me, cost or to satisfy more houses. Other case could be I can say, let's look at the four houses. Sorry, I think I don't have probably missed that four houses. So we'll give that, that's okay. Consider other case, let's say you have an n task to be done and you have an infinite supply of machines. And it's something like, let's say you have number of classes to be done. N task is number of classes to be conducted and supply machines like classroom. Now we want to see, and each classes have been given different time, how to want to schedule the classes so that you use minimum number of classrooms. And that's the objective. So each task has a start time. So task is a class. So each class starts at time Si and completes at time Fi. And in any classroom, we can't schedule two classes if they overlap. But we can schedule two classes if they don't overlap. And this is what we call is processing interval. So objective is how do we schedule this task so that I use minimum number of machines, or how do I schedule my classes so that I use minimum number of classrooms, and that's the objective. And we look at, so one feasible solution is take one classroom for each class. So if I have 10 classes, I end up taking 10 classrooms, which certainly not optimal, got too much cost. If let's say none of the classes overlapping, I need one classroom is good enough. So let's look at a practical case where some classes overlap, some do not, and how do we schedule it? So look at the problem following. Assuming a 7 tasks given here. Task 1 start at time 0, finish at time 2. Task 2B start at time 3, and it will finish at time 7, and so on and so forth. So a given 7 tasks A, B, C, D, E, F, G. How would you like to schedule using a greedy approach, and then see how you like to do that. So what should be greedy approach? There are two ways. You can basically pick up one task, schedule it. If the machine is empty, if you can look at any machines available, use it. If no machines are available, take a new machine. So first time, you always take a new machine. And when you get second task, you see is the machine available, schedule it. If it is not, don't then take a new machine. So objective is use old machine as much as possible, but you cannot use the old machine already running. So let's look at how do we approach. So typical machine assignment, first we should sort the task as per start time. So if you look at previously, the tasks are A, B, C, D, E. Task A starts at 0 and task F starts at time 1. Task B starts at time 3, and so like task G starts at time 6. So first let's sort this task based on start time, and sorting my task at A is the first task, then next is F starting at 1, next is B, next is C, then next is G because G is smaller. So I sorted them as per the start time, and now a schedule looking at the start time. So first task is A, there's no old machines, I schedule the task A, I get the task A which takes 0 to 2 hours. Now I take the next task F. Now I have one machine M1 being used. Machine M1 is busy till time 2 o'clock, 2 hours. That means I cannot use machine 1 for F. So for machine F, for task F, I use second machine and schedule 1 to 5. At this point in time, I have two machines being used. Now come to task B. When I come to task B, it starts at 3. It starts at 3, meaning machine 1 is available. So I should be able to schedule task B from 3 to 7 here. And this old machine I can use and don't need to take a new machine. So this is my task B. Now come to task C. This is my task C. Start at 4. You look at time 4. Both machine M1 is busy because at 4 M1 is busy. Machine 2 is also busy. That means I cannot schedule this machine at this time. I cannot use both the machines. So I need to take new machine, and I'm taking a new machine starting at 4 to 7. And this is what we basically do. And then I get task G, start at 6. At 6, if you look at time 6, my machine 1 is busy, machine 3 is busy, but machine 2 is free. So I can schedule 6 to 8 task G, and that's what I basically do. And then look at the task E, start at 7. At time 7, machine M1 is free, machine M3 is also free. I can pick up whichever one I want and task schedule E 7 to 10. And then I task 9. 9 can be scheduled both at machine 2 or machine 3. And so you look at what we have done. We basically, how many machines we need? We needed 1, 2, and 3 machines. Is there other way to approach it? We can look at that way. If we sort as per, we started this sorting as per the start time. If we sort as per the finish time and do that, and this exercise for you to see, does it work out? And then will you prefer by start time or finish time? Work out yourself. Let's look another set of configurations. We need to sort as per n times. It is n times. So 2, 4, 5, 6. So when I sort as per n time, look, task B is done later, even though task B starts at time 3, because task B finishes later. So I'm sorting as per this. So first I schedule task A 0 to 2. Now next is task F 1 to 4. I cannot use machine 1. Machine 1 is busy. So I'll take machine 2 for F. So F gets 1 to 4. Now C is 4 to 5. I can use M2 or I can use M1. So I take the which is the most ideal one. I is M1. Now task 3. B starts at task 3. Now I cannot use M2 because at time 3 M2 is busy, and I cannot use machine 1 because between 4 to 5 this is busy. So for task B I need to use another machine 3 and go ahead and then proceed G. Similarly proceed E and proceed D, and you look at, I still end up taking 3 machines. Is that the best we can do? Can you schedule some way so that we can live with only 2 machines? So if you look at in this case, if I were to schedule this task C, not at machine 1, but if I were to task schedule C here, then my this task B could have been scheduled here. And I could have actually managed only with 2 machines. So when see, if you sort them as per start time, if you sort them by finish time, does it always work? We need to look at, so greedy approach may not give me optimal solution. So I'll give you the way it works out. If I were to sort n time, but schedule as per the start time, I'm able to do with only 2 machines, same task. So look at what we did. If you sorted it as per the start time, scheduled as per the start time, we took 3 machines. If we sorted as per n time and scheduled as per n time, we still got 3 machines. But if we sorted as per n time, but scheduled as per the start time, we work with 2 machines. Does it always work? We need to explore, look at, and primarily, this is what I'm saying is the greedy approach. So again, same way you can look at the algorithm. So my suggestion would be write your own algorithm for machine assignment. Take this problem, write an algorithm, take different combinations. Examples are given in a book, work out those, and that will consolidate your knowledge. So basically, what we have done is we look at the basic greedy approach, we look at the coin change problem, we look at the machine assignment problem. So I would say another is if you are given only with one machine, like you are given only with one classroom, how many classes you can schedule? So write a problem or write a program to solve that, work out an algorithm, or other is find the largest number of tasks that can be assigned to this machine or given classroom, what the maximum number of classes you can have is the one exercise you should do, and what should be a greedy approach, work that out. So what we discussed today is a greedy approach. Look at the best immediate next available solution, even though may not be optimal. We applied to coin change problem and we saw that greedy approach sometimes may give optimal, sometimes may not give optimal, sometimes it may not even give me a feasible solution, all of it. But it is very simple to implement. We can go ahead do that, and we look at machine task problem. I also give you my own concocted water container problem. So both the coin change problem and machine task problem are taken from the book. Water container design my own, and that's the way we work. So with that, given you basic approach of greedy algorithm, and next time we'll basically get into more into details. We'll look at knapsack, other kind of problems. So my recommendation is work out the exercises and we'll continue discussing it. Any questions, please feel free to ask, and I'm done otherwise. If any questions you got, let me know. Otherwise, we'll close the lecture. If no, thank you. I'll stop and we'll continue. Our next class would be on Tuesday, 9 a.m. same time. We'll continue with greedy approach.